All right, I'm ready to start talking.
Yeah. Woo!
Okay, so the problem I want to look at today is a problem of connectedness. Now, for those of you who took PMath 351 last term, this problem, you're probably very intimately familiar with this problem, and you probably hated it. And I'm going to go over it today. I'm going to make you revisit your memories. It'll be great. So, I said that we're going to be dealing with a problem of connectedness, and so I should probably explain what connectedness means first. So, for this problem, we're going to be working in R2, our favorite vector space. And in R2, what connectedness basically means is if we have a set, call it A, and let's say it looks like this little blob, if I can split A into two parts, disjoint, that don't touch, then I say it's disconnected. In this case, I can't do that with A. It's just one big piece. I can't separate into two disconnected parts. And so I say A is connected in R2. However, if I'm dealing with a different set, say this is collectively A, this is disconnected because I can separate it into two parts which don't touch. So this is going to be our definition of connectedness. And the question that I want to ask and answer is, let's let A be the set of all A, B, C, D in R4 such that AD minus BC equals 1. My question to you is A connected? It's a hard problem. We're not going to answer that problem. I want you to take that definition I just gave you of connectedness and take it out of your memory and forget about it. We're not going to be answering this problem. We're going to answer a different problem. Let's make a completely different problem. I don't like this one. Let's ask if A is path connected. So I should probably tell you what path connectedness means. So path connectedness is completely different from connectedness. Now what it means for a set to be connected, we'll work in R2 first and then I'll give you a more general description. In R2, what it means for a set to be path connected is, given any 2 points in my set, can I draw a line between the points that stays in the set the whole time, right? So in A, I can do that because any point I pick, I can draw a line between the two things. If I was working in something like this, where it's disconnected, I shouldn't have said that, then I can take 2 points and, well, I can't really draw a line between them, right? Now, I'll give you a more formal definition here too. So, in more general spaces, the idea is, if we're working in a space other than R2, the idea is, can we take, for any 2 points, can I continuously deform this point into the other? And that's sort of the idea. Can I sort of take this one point and slide it along or continuously morph it until it reaches this other point in A? And I want all of those in between sort of morphings of that point to stay in my set. I never want to leave. So I'll give you the more official definition of path connectedness. We say that a set A is path connected if, for all x and y that I can choose in the set, I can find some continuous map, we'll call it F, from 0, 1 into A, such that f of 0 equals x, and f of 1 equals y. And this agrees with our intuition from before, right? So if I'm dealing with a set like this, then I can think of my map f as being the line. So as I sort of, have this interval from 0 to 1, as I sort of move along, I can draw this line until I get there, and that's my map. So that's some good intuition. Now, I'm going to claim, with no justification whatsoever, that path connectedness actually implies connectedness. Always, no matter what. If you have path connectedness, you'll always have connectedness. So it turns out this is such a new problem. If we can say that A is path connected, then we also have that A is connected. And that's pretty good. So, this set kind of sucks, right? What the hell does that look like? It's a 4-vector, AD minus BC equals 1. I don't even know what the fourth dimension looks like. I don't know about you. I certainly don't know what it looks like for a vector to have this kind of condition, that AD minus BC equals 1. So, how can I imagine to continuously deform one vector into another while staying in the set? That doesn't make sense. So I'm going to make a little mistake here. and I'm gonna juggle around my symbols a little bit. I'm gonna write this, and since I juggled those around a little bit, I'm gonna replace this with an M2R. So all I've done here is I've taken this ABCD vector and I moved the CD down here to make a matrix, and I replaced R4 with M2R, which is the set of all 2x2 matrices. Now, if you haven't seen this before, and most of you probably have, you've taken some basic linear algebra, that looks an awful lot like the determinant formula for a matrix. So if we let this be the set of all B equals that, then this is the set of all 2x2 matrices such that the determinant of B is 1. And suddenly we're working on something a lot more concrete here. We can visualize this. I hope you know what a 2x2 matrix kind of looks like. The way we can visualize a matrix in R2 is how does it act on the basis vectors, right? So if this is R2, then I can sort of imagine a matrix, say we're dealing with 1, 0, 1, 1. That's going to look kind of like this and like this. So what it does is it takes the first basis vector and does nothing with it, and it takes a second basis vector and maps it there. And so I can imagine this vector as this sort of, or this matrix as this sort of parallelogram that gets formed here. Now, you might have seen this if you've seen a 3 blue 1 brown video, or if you've heard this from a friend, but there's actually a neat relationship between the determinant of the matrix and this little parallelogram here. And we're kind of leaving analysis territory and crossing into linear algebra here, that's kind of the fun part. So the determinant of the matrix is actually completely related to the signed area of this parallelogram. So for a matrix to have determinant 1 means that the area of this parallelogram defined by the basis vectors is actually 1. And this is really nice. This gives us a very concrete way of picturing this set that was previously completely abstract. And now we can tie it to 2x2 matrices. And you might say that's kind of unrigorous to work with this new set around the old one, but there are some more ways. It's the same thing. I moved the letters, right? So I want to show basically that for any matrix I pick in this set, I can continuously deform it into a different one. So for example, if I pick this matrix to start with, I should be able to continuously deform it into the identity. And you can kind of see how I can do that here. Now, I'm not going to actually specifically define what it means for a function to be continuous in this space, but for those who have studied this, I'm using the G2 metric. For those who haven't, it's really the same way you expect it to apply. I'm just sort of slowly transforming things in a way that's smooth, in a way that isn't having any sudden jumps, such that like a small change in the input gives me a small change in the output, right? And so if you want to picture a way of continuously deforming this into the identity, I'm basically just going to be able to take this and just sort of drag it over here. If I just take this vector defined by this second half of the matrix and I just drag it over, I'm going to get the identity. And if I do that, I'll preserve determinant all the way because the area is defined by the base times this sort of height. I'm not changing that. So that's one possibility, but there are other possibilities. And this is sort of might seem a little overwhelming because I have to take any matrix and deform it into any other. But I'm going to give us an easier time. I'm going to say, I'm just going to pick an x, and I can find a continuous path that takes us from x just to the identity matrix. I'm not going to care about any y. And the reason this works is because if I can find a path from x into the identity matrix for any x, and up to relabeling I can find a path from any y into I2, the identity matrix in R2, then I can find a path from x to y by just taking that path from x to I2, and then taking that reverse path from y to I2. So I go from here to here, and then like from here to here, by just taking the reverse path. And that'll give me a path from x to y. So I actually only need one variable here, and I only need to be able to continuously deform any particular matrix into the identity. So what kind of deformations are we going to be dealing with? Which word should I use? I'll stick to the middle one. We're going to go use this one. So there are three kind of deformations we can have when we're dealing with a matrix of this type, because determinant is 1, so we have a sort of niceness. The first kind of thing we can have is we can have a scaling. So that can be like, if instead of dealing with something like this, maybe the length is shorter this way, but it has determinant 1. The other thing is we can have a rotation. So that would be like if I was dealing with something like this, where this is both of our basis vectors defined by the matrix. I'm just taking our identity and I'm rotating it, and that would be a rotation matrix, and that's one of the transforms we can do. And the last one is a shear. And a shear is kind of like rotation, but I forgot to rotate one of the basis vectors. So if you want to picture, it's something like this, where maybe I had something like this, and I just rotated this and forgot about the other ones. So if I want to transform something into the identity matrix, I just basically have to undo these three transforms. That's all there is, right? So I have time. Let's try and do that. So what's the first one I want to tackle? Let me see my paper. I'm pretty sure it's orthogonal, right? So the first thing that I want to undo is any shear. So the idea is I want to get from a matrix that might look like this, rotated in some way, I want to make it orthogonal. So I want to sort of slide, no matter what this is, I want to sort of slide this over so that it's orthogonal to the other one. I don't really care about height right now, I just want to make it orthogonal so that they're at 90 degrees to each other, right? And there's actually a process for doing this in linear algebra. If you've taken Math 235 or Math 245, you've probably seen something called the Gram-Schmidt procedure. And what the Gram-Schmidt procedure is useful for is doing exactly that. We can take any basis in R2, or any linearly independent set, I guess, and we can take that and get an orthogonal set out of it. And the way that the Gram-Schmidt procedure works intuitively, you don't actually need to know the mathematics behind it, I'll just explain it here, is say that these are our two vectors, and they're linearly independent, but they're not orthogonal to each other. Well, we can get an orthogonal set very easily, because if I just sort of take the shadow drop down from this vector onto this one, this vector is going to be orthogonal to this one, right? If I just sort of shift it over here, then if I just sort of take one component of this with respect to this one, I get an orthogonal set. And so what this actually looks like mathematically, say if this is U1, or we'll call it V1. Say if this is V1 and this is V2. And in fact, let's get into the math, right? Because we're starting to work with symbols here. So let's let V equals ABCD be a matrix in A. So it's just a 2x2 matrix that satisfies that determinant requirement, right? And let's say that we can alternatively relabel these column vectors as U1 and U2. So U1 is just AC, U2 is just BD, right? And so, did I use U? Yeah, okay, I used V. Okay, I was right the first time. So we'll call these V1, I'll call this V2, right? And let's say it looks something like this. Rotated doesn't really matter. The way that we'll get our orthogonal set is we'll just take V2 and subtract off this sort of projection bit, because this bit right here, the short of shadow under it, is actually called the projection of V2 onto V1. And there's a formula for it. So since our V2 is BD, this is going to look something like, let's call our sort of orthogonalized vector U2, and V1 won't change, we'll say it's just U1. Or to transform this to move it that way, we'll do BD minus that projection, and that's going to look like U1 dotted with U2 over the norm of U1 squared times U1. You don't have to know what this means, I'm just doing the symbolic manipulation. But if you expand this out, you'll get that this equals B minus A times AB plus CD, and D minus C times A squared plus C squared. Then, if I make a matrix C that has this one untouched, because we don't actually want to touch this one, we just want to get a new orthogonal vector here. So this is still going to be AC. And here we'll have our new kind of transform basis vector here, which is orthogonal U2. And I'll just copy that here. AB plus CD. And this is C. I think I used C, right? Did I use C? Oh, wait, no, it's D. Minus C times A squared plus C squared. So we have our end matrix and our start matrix, right? So we have the original thing and we have the kind of resultant orthogonal matrix we want. But this doesn't really give us all the in-between, because the whole point with path connectedness is we want to sort of continuously deform this vector into the other. We want to take this arrowhead and slide it over here. And the way we can do that is by playing a pretty easy game of just, let's, linearly just keep subtracting this off bit by bit until we get there, right? So we can do this pretty easily. I'm going to change this from C, and I'm going to define a map, alpha from 0, 1 into A, defined by alpha of t equals this stuff. I'm going to drop a t here, I'm going to drop a t here. I threw my chalk away. And this is actually going to give us a path that continuously deforms this vector into this vector. Because the way you can think about it is we have sort of our original matrix A, B, C, D here, and over the course of t from 0 to 1, I'm just slowly subtracting off this projection bit until I fully get over here. At 0, nothing's subtracted off. At 1, the whole thing's subtracted off. So that alpha of t equals b, and alpha of 0 is b, and alpha of 1 is, we'll call it c. So that does one thing. We're a third of the way through. Let's try the rest of it. What did I say the rest were? So we undid our shear, and the last few things we have are scaling and rotation. Let's say I want to undo the scaling now, because although I fixed it so that it's orthogonal, I still might have something like this, where say this is really short, this is really long, and I want to sort of shrink this and elongate this so that they both have length equal to 1, because that's what the identity matrix looks like, right? So I'll move over here. So let's say that the C we have from over there, we'll relabel it and call it EFGH, right? And we also called it U1, U2, where these are kind of vectors, maybe like the little hat. And we already know that C is orthogonal by Schmidt, which we just carried out, and we just want to normalize it. So right now, we know that whatever we have, say this is U1 and say this is U2, we know that since the determinant is 1 and it's a rectangle, that means the area has to be 1. So these two things must multiply to give us 1. So we must have the norm of U1, and the norm is just length. So if you've never seen that before, it's just the length of U1 Pythagorean theorem times the length of U2 must give us 1, right? So if we scale this by a certain factor, we're going to want to scale this one by the inverse, because the idea is in our end matrix, which let's say we're going to transform C into D, which is going to be our normalized matrix that has both lengths 1, we're probably going to want to scale U1 by 1 over its length, so that we get a vector of length 1. And if we do that to maintain this sort of relationship, we'll scale U2 by the norm of U1, right? And so we already know what we want our last matrix D to look like. If I'm going to define this to be a map theta from 0 to 1 into A, I already know that I'm going to want B of 0 equals C, and I'm going to want theta of 1 to equal this. So, the matrix defined by 1 over U1 times U1, and the other one to be the norm of U1 times U2. But I want to do this in a continuous way, and I'll be a bit more explicit about it. So the actual function I'm going to define, I'm going to give the definition, and I'll give you the intuition. It's going to look something like this. So E times 1 minus T minus, or plus T over the norm of U1. First element, G will be similar. And then we'll have our F and H there, but I'm going to do something else here. But I'll explain this sort of column first. This sort of might seem arcane, it's just a bunch of symbols, but it actually makes a bit more sense if I expand it out into E times 1 minus T plus E times T over the norm of U1. And now in this form, you can see I'm actually playing a similar game to what I was playing way over there when we were doing the orthogonality, right? Because at T equals 0, this term is going to vanish entirely. And this term is going to be fully present, E. So I'm just going to E plus 0. Whereas, as I take it from 0 to 1 slowly, I'm getting less of this term, and I'm getting more of this term. So I'm slowly transitioning E into E times 1 over the norm of U1. And I'm doing the same thing with G. So since EG forms that first vector U1, I'm slowly scaling it by sort of slowly subtracting off one part that I had originally and one part that I want to get it to. And then, as you might expect for our U2 here, as I said here, we'll want to multiply its length by the inverse. So I'll do the same thing. We'll just take the inverse, right? Because I want to maintain that determinant, that multiplication of their lengths being consistent. And it turns out that this is also continuous. Now, I will leave the proving of that and this being continuous as exercises to the readers who know how to do analysis. Because I don't, who cares, right? So this will actually work. And the idea, I won't show you like explicitly algebraically why I preserve determinant. But the idea is obviously, again, since every time we're multiplying this and shrinking a little, we're growing this a little bit so that no matter what t is, we're always maintaining that their area multiplies out to 1, right? So over there, we're maintaining determinant 1. Over here, we're maintaining determinant 1. And our beta, our alpha are good. They still don't get us all the way though, because we have a rotated matrix. We don't have the identity, and I hope the identity doesn't look like this, that would suck. So, erase this, and we'll get to the last part of this, which is undoing the rotation. Now, this is actually easy. Maybe it doesn't seem that way, but it's actually like dead easy. So we've transitioned B into C and C into D, and we know that D is now just a rotated, I guess like unit matrix in a way. But then we know that D is going to look like cos of theta, negative sine of theta, cos of theta again, for some theta in 0 to 2 pi, right? And if you haven't taken linear algebra or you haven't seen this yet, this is just what a rotation matrix looks like for a particular angle. So like, for pi over 4, it would look something like this, with this being sort of the original identity matrix, and we just rotated it 45 degrees. And so we know our D is going to look something like that. And if we want to unrotate it, well, we just slowly need to transition whatever this angle was to 0, because the identity matrix is rotated by nothing, right? So this is actually pretty easy now to define. Let's define gamma, which takes us from 0, 1 into A. And we'll play the same game we were doing before. We're slowly kind of, as we go from 0 to 1, slowly going from subtracting nothing off to subtracting the whole thing off. So we'll define it by gamma of t equals cos of, I think I did, what did I do? It was t theta minus theta, I think. So I'll just make sure. Yeah, so theta minus t theta, negative sine of theta minus t theta, and the same thing for all the other things. It's the same rigmarole. Cos theta minus t theta. That's our matrix. We'll start with theta of 0 being d, because these things will go away, and we'll just have cos theta, negative sine theta, and so on. And we'll have gamma of 1 equals theta minus t theta, which is, since t is going to be 1, all these are going to go to 0. We'll just have cos of 0, sine of 0, and so on. That is going to give us 1, 0, 0, 1, the identity matrix. So I could call it done here, but let's put it all together. We've done a lot of work, right? So let's put it all together. Let's define our full map f from 0, 1 into A. I'll define it piecewise. Let's say the f of t is defined to be alpha of 3t if t is in 0 to 1/3. And I'm just doing basically scaling it. I'm saying, okay, I have 0 to 1, and so for the first third of that interval, I'm going to do the work of orthogonalizing it, and you'll see for the second third, I'm going to do the work of normalizing it, And then for the last third, I'm going to do the work of unrotating it. So in the other part, which is 3t minus 1/3, that'll happen in the 1/3 to 2/3 interval. And the last thing, gamma of 3 t minus 2/3 if t is in 2/3 to 1. This doesn't. F of 0 equals b, f of 1 equals the identity matrix. And so we can say with absolute certainty that yes, that's set A that's no longer on the board is path connected, and hence it is also connected. That's the result. I might have spent a little too much time on the workings, but the whole point of this is just to demonstrate that analysis is very fundamentally visual, and a lot of people don't like analysis because it's very abstract. But everything that you do, all of the algebra sort of funky symbolic notation stuff we did here, it was all tied to intuition about dragging things around, about transforming things in a continuous way, about doing smooth actions. And I think that's what analysis is all about. And once you kind of see through to looking at things and drawing pictures of blobs on a board, it makes solving problems a lot easier. So yeah, that's it. So if you have any questions about that, then please ask. But okay, 2 questions. Jerry?
So is A connected?
What was that?
Is A connected?
Yes, because the whole thing we spend all this time doing is showing that A is path connected, right? Because we can continuously deform any matrix we have into the identity, and then undeform the identity into any other matrix. So it's path connected, right? And I presented as a completely, maybe not true seeming at first fact at the start that path connectedness implies connectedness. It's a stronger form of connectedness. In the vector spaces we care about, they're actually equivalent, but in this case, I'll just say one implies the other. Yeah?
So I mean, most of the talk that we've been spending time like splining between 2 matrices, so like 1 times the original plus 1 minus t times the other, or something like that, and then we just like slide smoothly.
Yes.
And like, you know, like you did it for like the 3 specific types of transformations, but we could probably do that a little more, I guess, generally in a sense. Like, could you just take A, and then the identity, and then like, I mean, okay, the determinant will probably get messed up, but is there some kind of more, just like, like, you know, for n dimensions, we're gonna have more than 3 types of operations, right? So I'm trying to think like, how would we go from, you know, like n17 and like try this kind of same, like, you know, spline it around a bunch to get where we want.
Right. Yeah. So you kind of have to do it in long form because you can't just immediately just kind of linearly interpolate between your starting matrix and the identity, because the determinant will get messed up and you will leave the set. I tried that as the first kind of attempt at this problem. It didn't work. This technique would actually perfectly generalize to higher order matrices. So if we're working with 3x3 matrices, theoretically this would work just as well, because in fact for those matrices as well, if your determinant is 1 or greater than 0, then the only kind of transformations you're going to have are shears and rotations and scalings, just maybe on multiple things. But the Graham-Schmidt procedure that we looked at generalizes also to Rn. You can actually continue the same process if you have like a set of n basis vectors, just by sort of having each one piggyback off of the work you've done so far. And have you learned about Graham-Schmidt yet?
No.
Okay, yeah. Yeah, so that's the idea. You sort of like, if I'm having like 2 vectors here, and maybe one of them like goes forward, then you sort of get one with respect to the other, and then you get this one with respect to both of them. And you sort of inductively continue that until you have a full orthogonal basis.
I see.
So the process fully generalizes. I just picked an easy one because it was on the assignment, and also it's easy to show the work.
Makes sense.
Yep.
Is there, this isn't that related, but is there an example of something that's connected but not path connected?
Connected but not, yes, there is. Let's look at this graph. And we're going to look at the set of all x and f of x pairs, where f of x equals, I think it might be sine 1 over x. And someone who knows analysis can correct me if I'm wrong.
Yeah, it's like 1 over x. Good.
Good, okay, yeah. So basically the function's gonna look something like this, and it's gonna start oscillating really wildly as we get here. It's actually never gonna touch 0, it's gonna be undefined, right? And then kind of mirrors it this way on this side. And you can actually prove, and I didn't give the definition of connectedness because everybody hates working with connectedness. It's a really ugly definition that's very set theoretic. But you can prove that this set is connected. However, it's not going to be path connected because if I want to get from here to here, I kind of need to travel an infinite distance to get across because it just fluctuates so wildly and infinitely here. And that's the general idea of the proof. So this is sort of the canonical example of a set that is of a space that is connected but not path. Is that?
It's only connected if you mean it with like 0, 0, right?
Oh yeah, sorry.
Oh yeah, and like f of 0, 0. Yeah. Okay, piecewise. So okay, thanks for pointing that out. Anything else? Okay, we'll say that's it. Thanks for everyone for coming to SASMS.